Welcome back to ECE 442-542. I have a lot that I would like to cover today, and we'll get started with announcements. Homework 5 is now available. After today's class, you'll be able to do half of that, but it's not due until a week from Monday, which is a little bit off our normal schedule, but that will give us a little bit more time to hopefully get the material covered that we need covered for homework number 5. Exam 2 is, no. Exam 2 has already occurred. I wish I could just return it again and grade it on a weekend again. That would be nice. But we have exam number 3 scheduled for the 15th of April. This Friday, I have another commitment in the department, so you'll see me around, but I can't be in office hours on this Friday. But I'm thinking those of you that are here won't be needing office hours. The others might just come collect their exam if they haven't yet collected exam number 2. In terms of what I would like to cover today, let's summarize these performance specifications. Those are really rules of thumb, or just what we're hoping to maybe get close to when we're doing this design. It just gives us a starting location or a starting point with which to try to build a desired transfer function T sub c of z. It's not like these are hard and fast and they're exact and precise and that they'll always be right on, but these are just rules of thumb that guide us in the selection of a two-pole system. We'll then build a constraint table if we're given a couple of those performance specifications, what we can then determine in terms of our radius and angle for those z-plane desired poles. We'll look at that via a step response in MATLAB just to get us comfortable with doing some of this in MATLAB. We'll look at how to display some of those regions in the z-plane or inside the unit circle relative to constant zeta lines or constant damping ratio lines. That is produced with this z-grid function in MATLAB. We will then talk about, we've sort of just said, here's a sample period. Let's now talk about how that relates to the sampling frequency. That's pretty clear, I hope. If we have a sample period, how to relate that to the sampling frequency, but then how the sampling frequency is related to the Nyquist frequency. And if we're not obeying, or if we have frequencies above the Nyquist, those frequencies will now alias back to frequencies between DC and the Nyquist frequency, and it's nice to know that is possible, and that's why we want to sample fast enough to avoid anything like that happening, is the idea. Then we'll look at an example where maybe the performance specifications are incompatible or inconsistent, meaning you might be given a percent overshoot spec, a settling time spec, and a peak time spec, and those three may not be compatible together simultaneously, and we may have to then constrain one more than the others in order to make the three work together. So they may not want to sing together without some modification. Ultimately, we will get into controller design as I had promised, but before we get there, we have to feel comfortable with specifying these desired transfer functions that we're calling capital T sub c of z. Let's then quickly summarize these three different performance specifications. We have the first one, let's say, is the settling time, which that R is our radial distance of the dominant poles. N sub s is the number of sample periods, and that's derived by saying x at time N sub s needs to be 1% of where we started. That's where that relationship comes from, but that's the key relationship that we can then use to derive these two formulas that allow us to relate settling time and radius, and settling time specified in terms of sample periods if we are given the radius to start with. So if somebody says, oh, here are my closed loop poles, what's the settling time? You can use this second formula to determine how many sample periods it's going to take to reach a 1% settling time. Given T sub s, we can then pull out, if we need to, the number of samples, capital N sub s. Once we have that, boom, our radius is given by raising 10 to the minus 2 over N sub s, all of that coming from the black equation up above. If we're given R, then we can back out the number of samples using that same relationship, just solving for N sub s instead of R. That's this settling time specification. The percent overshoot specification, if we're given the percent overshoot and we need to determine zeta, you could use a figure, a diagram, if you wanted to. You could do it pictorially, or you could do it with this formula. Or if you're given zeta, or you've calculated a zeta based on your particular closed loop poles, then the percent overshoot, again, this is for a two-pole system. The overshoot of that underdamped system would be 100 e to the minus zeta pi over the square root of 1 minus zeta squared. We've looked at then the settling time, percent overshoot. We had the peak time that we were interested in also as a performance specification. The peak time was pi over omega sub d, where omega sub d was the vertical distance in the S-plane. That was the imaginary part. We can relate that damped frequency of oscillation to our digital angle, theta sub d, by simply saying or recalling that theta sub d is omega sub dt. If we combine those, now we have a way of relating our peak time to theta sub d, our angle in the z-plane, where peak time is pi t over theta sub d. That allows us then to say, if we're given the peak time, depending on how we're given that, if we're given that in terms of an absolute number of, let's say, seconds, then we might need to know the sample period. If we have the sample period, we can get the number of samples to reach the peak, and N sub p is then pi over theta sub d, which allows us then to just solve for theta sub d. If somebody gives us the peak time, we can now figure out what the angle of those dominant poles need to be relative to that peak time expressed as a number of sample periods. If we're given the angle, then we can compute the peak time. Time to peak is then pi t over theta sub d, or if we want it in sample periods, if we don't know, maybe the sample period is unspecified, we could calculate the time to peak and the number of samples by dividing theta sub d into pi. Those are our three different performance specifications that we've introduced. Here's a table in which we might be given two of those, and we need to find the dominant poles based on those two specifications. You can derive all of this, but now if you're given the settling time, that's related to the radius. You can find that radius r. If you're given the percent overshoot, you can compute the value zeta, the damping ratio, and now you can compute r is just what you calculated. Theta sub d you can find in terms of r and zeta by relating the parameterized form of those poles that we've seen in earlier or in last time's lecture. But now you have r and theta sub d, you can find z sub d. Similarly, for given the settling time and the peak time, or given the percent overshoot and the peak time, you can figure those relationships relating R or finding R and theta sub D given the specified values for performance, either settling time, peak time, or percent overshoot. Let's look at applying that to finding. Let's now use these concepts to actually build a desired closed-loop transfer function, and that desired closed-loop transfer function, let's just call that T sub C of Z. That might be our controlled transfer function later, and that's why I'm trying to use the same notation for that transfer function. What we want to do in this example is build that T sub C of Z, and I'm assuming it's a second order transfer function, and plot its step response in MATLAB for a system that has a peak time of 10 samples and a settling time of 30 samples. So I really haven't specified the actual sample period. I wouldn't have to, but I'm going to, just to give us something to play with. But you can, in MATLAB, specify an unspecified sample period by using a -1 in the function's argument that's looking for the sample period capital T. You could simply say, oh, my sample period I don't know, or it's not necessary to specify. I'm going to just say -1 inside MATLAB. But here, let's go ahead and assume that, so we want to now try to build this T sub C. Let's just go ahead and assume or suppose our sample period is 10 milliseconds, or 0.01 seconds. We were given time to peak in terms of, what were we using before? Actually, number of samples. So maybe I should say N sub P is equal to 10. Is that the notation I was using before? And we were also told that for the settling time, we were given N sub S is equal to 30. And now that we've given a specific value for the sampling period, we could compute a numerical value for the settling time. That's just 30 sample periods. Or when we start to simulate this, hopefully our response will be within 1% of our final value when we do the step response after 0.3 seconds in MATLAB. That's what we now are assuming when we supposed a sample period of 0.01 seconds. Given the settling time spec, what parameter of our poles, or of T sub C, I've already told you what it is, the poles, what parameter of our poles will T sub S give us? Or what do you see on the z-plane diagram if somebody now gives you the settling time? If they give you a settling time, what are you thinking, or what are you visualizing relative to the z-plane? Now you see a target, don't you, or these concentric circles. The radius is now indirectly specified by this settling time specification. Let's go ahead and find that. You could just find a formula, but you could also, let me just go ahead and rederive that. We know this relationship, that's based on the 1% settling time. We can now take the log base 10 of both sides and now solve for R. And I've already calculated that to be 0.8577, which makes sense. I mean, it's less than 1. If we have a settling time, we better have a radius inside the unit circle. If you get something outside, you might say, ooh, I've punched something in wrong, or I've done something wrong if you have a number greater than 1, if you're talking about a settling time. Then we also know our peak time is pi omega sub d. And what's the peak time associated with in terms of our picture on the z-plane? We've now found the radius from the settling time. What are we expecting from the peak time? A logarithmic spiral, an angle. This is going to give us theta sub d, and theta sub d is related to omega sub d. Theta sub d is this omega sub dt. Putting those together, we now have time to peak as pi over theta sub d over t, or that's pi t over theta sub d. And we were told that we wanted our peak time to be 10 samples, so now we have 10t must equal pi t over theta sub d. We can cancel the t's. That's why we really didn't even need to know the sample period, but we put one in just to give us some numerical values on our time axis later. Now we can solve that for theta sub d, and theta sub d is 1/10 of pi, or 18 degrees. We're 1/10 of the way around our unit circle, and we're at a radius of 0.8577, if I remember right. That's now our dominant pole pair. Z sub delta is now this r e to the j theta sub d. That's the 0.8577 e to the j pi over 10, or if your calculator is in degree mode, you may want to use the angle in degrees. You can now put that into rectangular form using the cosine and the sine of 18 degrees, and you end up with z delta being equal to 0.8157 plus and minus j. So now I'm introducing the conjugate of 0.857 times the sine of 18, which ends up being 0.2650. Where I've simply used this is r cosine theta sub d, and this is the r sine theta sub d. Hopefully I haven't done anything magical. Are we okay with this information? With the given information of a peak time of 10 samples and a settling time of 30 samples, we've now arrived at 2 poles that we want to have inside our transfer function. And we can put those in directly. We could say, okay, now we have z minus 0.8157 squared plus 0.2650 squared. We said we wanted a second order transfer function. This is now a second order transfer function. We didn't say anything about the numerator, but let's go ahead and assume we have a one-step delay between when we excite this system and when we start to get a response out. let's just say that we have, and that would correspond to an actual time, 10 milliseconds. That means that we're putting a 0 right at the origin. And maybe we want this to be a nice transfer function in the sense of we might want to have a DC gain of 1 for this system. Meaning right now, maybe we don't know what we have some gain K. How will we force this transfer function to have a DC gain of 1? What Z value do we want to be thinking about if we're looking at a DC frequency? Z is 1, isn't it? If we now look at T sub C of Z with Z equal to 1, we want that to equal 1. This now says we have K times 1 over 1 minus 0.8157 squared plus the imaginary piece squared. That's pretty easy to solve for K. And K ends up being 0.1042. And now we have our transfer function. I'm not going to write it again. Let me just see if we can put that into MATLAB and simulate the step response. What was my numerator? .1042. 0.1042. Is that all I need for the numerator? Don't forget, I actually have, this is now 0.1042, but I have a Z term in the numerator. I don't just have a constant. And in MATLAB, we write these polynomials in row form. And to obtain a 0 at the origin, what do I need to put into my numerator expression now that I have the gain inserted? Do you remember? So now I need to say something like 1 comma 0. Does that look okay? Now I have 1 times Z plus 0 times 1. That's going to give me a Z in the numerator. And that's what I want. This is now the numerator expression that I want. My denominator is now going to be that mess multiplied out. So I now have T sub C, I guess I lied. T sub C of Z is 0.1042 Z over Z squared minus 2 times that 0.8157 Z plus the 0. Is that okay? Now, can you remind me what those numbers are? Now I have Z squared, 2 times, and this is supposed to be a negative, wasn't it? Minus 2 times 0.8157. And now this, I can do the first part. Let me just do it the easy way. Plus, what was the other piece? I can't hear. 2650. That wasn't the enemy. if you were watching my type. I don't know where my fingers were going, but it started to, let me just quit. So there's my denominator. I said I had a sample period of 0.01, and I can now create my discrete time transfer function, building my numerator and denominator with that t. And there's now my transfer function that I desire for my system that's supposed to have a a settling time of 30 and a peak time of 10 samples, or that will now translate into a peak at 0.1 seconds. And that's all from a step response. Wow, really? There is now my step response. And if I right-click on this, I could actually look at some of the characteristics. I could look at the peak response. That now tells me I have, and I'll now put my mouse over that, and I'll click with the left mouse to lock that information on. I'm peaking at 0.1, which is what I said. And now I can do a right mouse, characteristics. Let's do the steady, or let's do the settling time, which probably won't be the same that I want, because this is now looking maybe at a 2% settling time. And we were looking at a 1% settling time, but do you see that at 0.3, we're getting very close to our final value of 1? Does that look okay? And if we hovered over this, we could see that we were better than what they wanted for their settling time. Maybe a 2% settling time is 0.235. Questions on that? And you can use this now with your homework in checking your work, or I might ask you to sketch this in MATLAB or plot these transfer functions that you might generate. Question? So now if you don't use a sample period for your system, let's just say that we put in a new one. Let's say GC2 is going to be equal to num denom, and now let's say -1. That's what you say to MATLAB to say, whoops, what? Oh, I got to going too fast. I need a TF. I need to tell it what function it needs to be. Sorry. We all make mistakes. And now it says the sampling time is unspecified. If I want to put that in a different figure and say step, I don't know that I have the patience to wait, but I think this one will be quicker. Now do you see it labels the time as seconds, but you need to know that each of those is just a sample period. And in this case, it looks the same. Now after 30 samples, it's settled, and we've peaked at 10, so it labels the horizontal axis wrong, but that has units of sample periods. Is that okay? Is that what you were asking? No, it now knows it's so the question was, I was wondering if the curve would be a continuous and not have this jagged behavior, but we've told it it's a discrete system because of the -1 for the sample period. And it then knows that it's generating or using a discrete time transfer function. Other questions on that? Yes? How did I get a z in the numerator? For those of you that are listening to this, you have no idea how I found a z. I grabbed it out of thin air. I said that I wanted a 1 sample period delay between my input and the output, and that then says that I need a pole zero excess of 1, And a 0 at the origin is very fast. I didn't want to put a real 0 between 0 and 1. I just wanted to put it right at the origin. That's where that Z came from. And sometimes I might tell you on your homework, put a 0 at the origin. That's what I did here. I just knew that I wanted a one sample period. And look at what happens. Here, this is a step response. So it was hit when? At 0. When did it start to move? After one sample period. That's that one sample period delay. If you looked or put that transfer function into a difference equation where the input is, let's say, u and the output is y, you'll see that there's a one sample period delay between the output now and the input because of that difference in order between the numerator and denominator. That help answer your question? That's where that z in the numerator came from. I just decided that's what I wanted. Now, as a homework assignment, and this is not a formal homework assignment, but you might see if you can back out the percent overshoot given the r and the theta sub d. Can you now evaluate or solve for zeta and then plug that zeta value into your percent overshoot and see if the overshoot is consistent with this overshoot, which says it needs to be 21 and a half. And I think you'll find that the formulas that we've used, if you solve now for zeta and plug that into the percent overshoot formula, you'll get 21.5% for your overshoot. Questions on that? Now, before we leave MATLAB, I know you feel warm and fuzzy with MATLAB. Let's now generate these regions in the z-plane that you might now be able to plot your poles on top of. Maybe you now know that you have a zeta value of 0.7 and a radius of 0.7. You now get out your ruler, you measure a 0.7 radius, and you intersect that with your damping ratio or your logarithmic spiral with a value of 0.7, the zeta value of 0.7. Meaning, if we, did I do a new figure? I don't want to wipe out what I've just created. Let's create a new, and now if I just do Z grid and look at whatever figure, figure 3, ooh, isn't that neat? So there is your Z grid. What in the world is that? One, it's distorted, isn't it? Because your horizontal and vertical increments may not be the same. So you need to tell MATLAB, would you just wake up and make the axes equal? So we'll use the formula for that. We'll say axis equal. But do you see the logarithmics? Let me do that first before we start talking too much about this. So let me just, whoa. Axis equal. Feel like I'm issuing commands. Axis equal. So now we have the axis equal, and it may look a little bit better. These are now the logarithmic spirals that if you use your imagination, maybe they sort of look like a smashed heart on its side. But this is the entire unit circle. The other lines are actually natural frequency lines, and we're not using those in our constraints. But these are, in a sense, orthogonal guidelines, just like the angles and the radius are orthogonal in the S-plane for the percent overshoot and natural frequency. The logarithmic spirals are the percent overshoot lines. The other lines are natural frequency lines. What we would maybe like to do is get rid of those natural frequency lines. Or maybe you want to just pick a few zeta values. So you could go back and you could say, let me just have, well, let me put a new figure window in, and let me say that this is also axis equal. And maybe I just want to look at zeta values of 0.3, 0.7, and 0.9 just for grins. I don't know where those came from. They just magically appeared. Okay, I just said these are the zeta values I would like to see. And suppose that I don't want any natural frequency line, so I'm just going to say W is equal to 0. My parameterized variable for my frequencies, I'm just going to say are 0. I didn't need to display those. But now I could say Z grid of Z and W. And now I have, did I say axis equal? I did, didn't I? So that should look something like a circle. And if I wanted to, I could actually maybe even put the horizontal and vertical line in there by just sort of cheating a little bit and say x equal -1. Oh, let's make it a little bit fine, up to 1. And now let me say y is equal to 0, whoops, times that x, so that will, and I want to put that on the diagram that I just, or the figure window that I just had, so I'm saying hold that figure window. Now I want to plot x versus y, and I want a black line. If I don't say K for black, K, I guess K is in the word black, so that's where the K comes from. Because if you just said B, maybe you'd think it's blue or banana or something, but K is black. That's pretty obvious, right? So that's now our line, which I hope now that gives us our horizontal line between -1 and 0, and I could actually make another vertical line by just saying y and x, I hope. And there's now my xy coordinates. And if I just wanted maybe the top half, you know this is symmetric with respect to the top half and the bottom half, I could cut that off by saying let's just allow the axis to be -1 to 1 in the x direction and 0 to 1 in the y direction. And now I just have the top half of that plot. And now you could start putting your poles and zeros on that diagram for design purposes, for example. And I may just put some of these in the content page of D2L, and then you can print those out if you're having to sketch this throughout the semester. And you don't have to now rely on your artistic flair to put in those logarithmic spirals. You can just allow MATLAB to do it for you. Questions on that? All right, so let's move into another. I hope I'm following the script. I've about forgotten what my script was. But I'm going to assume that now we're ready to start talking about Nyquist and the sampling frequency. So let's look at the sample period with respect to sampling frequency, Nyquist frequency, and aliasing. And we're going to look at this by using or thinking in terms of S-plane to Z-plane mapping. And if we're looking at S-plane to Z-plane mapping, what are we using? What relationship? Our good friend, right? Z zest, I guess, with an equal sign in there. So if you're in the shower, you already know. Do they still make that Zest soap? This class has a lot of soap in it. We've already talked about Ivory. Now we're talking about Zest. Sorry, I don't even know the companies. I'm not marketing any of those. I don't have stock. Well, I don't know. I have stock in any of those companies, but I'm just trying to get you to remember the formula. Z is equal to e to the st. That's a zesty formula. And this now, by using this, we've just assumed that we have a sample period, capital T. This introduces a sample period. My lectures are kind of like a box of chocolates, aren't they? You never know what you're going to get, wherever that came from. All right. What does T actually do for us? Or what does that put on top of us? Does that introduce some constraints? And in fact, it does. It actually tells us sort of what we can expect to be seeing when we're looking at the results. So T, now get ready to write a little bit. T restricts the range of frequencies we can actually resolve or see. And I'm going to ask you to remember Nyquist in terms of this relationship. Nyquist is maybe omega sub n, but I may refer to that as the highest frequency, omega sub h, that we can resolve, and that's actually just half of the sampled frequency. Which, have you had a course where you've talked about sampling? Let's say that this is the magnitude of our signal that we are trying to sample, and let's say this is the highest frequency that we have. Well, once we sample this analog waveform, that just produces copies. And don't hold me to this diagram in terms of accuracy, but I just need the form. Now we have all these little triangles at every omega sub s, 2 omega sub s, 3 omega sub. That's what happens when we sample. And in order for these higher frequencies not to be reflected back and look like frequencies between 0 and omega sub h, we need omega sub h to be away from that particular point. And what is that point? This point is minus omega sub h. So this point right there must be omega sub h minus, omega sub s minus omega sub h. And we want those to not overlap. So that says that we really need to make omega sub s big enough. We need to make it big enough so that omega sub s minus omega sub h is greater than omega sub h. Or if we solve that, now we say that omega sub s is twice the highest frequency. And that's where that highest frequency comes from. We could solve this now for omega sub h, and omega sub h is now less than twice the highest frequency omega sub s. That's where that Nyquist frequency is coming from. Or, in words, omega sub h is the highest or largest frequency that can be resolved in a sampled waveform, where we're sampling it at a frequency omega sub s. If we actually had frequencies that exceeded or were higher than omega sub h, and we sampled at omega sub s relative to this being right equal to omega sub s over 2, then that frequencies higher than omega sub h appear to be between 0 or DC and omega sub h. That's with omega sub h equal to omega sub s over 2. Or frequencies above omega sub h are aliased or look like something else, and those higher frequencies appear as frequencies between 0 and omega sub h, which is omega sub s over 2. So now we're saying that that Nyquist frequency is actually that highest frequency omega sub h, which is omega sub s over 2. So if somebody says, what's the Nyquist frequency, and they tell you what the sampling frequency is, you can divide that sampling frequency by 2 and say the Nyquist frequency is half that sampled frequency. And the only frequencies that you will be able to identify in your sampled waveform are between 0 and omega sub s over 2, or 0 and that Nyquist frequency. Now, we are going to be playing with signals and transfer functions with real coefficients. Which implies that if we have let's say a frequency at omega sub s, let's say j omega sub s, we're now on the imaginary axis in the s-plane, we have its twin or its complex conjugate at its negative. For every j omega sub x, we have its complex conjugate minus j omega sub x. So let's see what happens, in fact, if, suppose that we are looking at, here's j omega sub s, well, let me do that, over 2, and here is now j omega sub s, and we have the corresponding minus j omega sub s over 2 and minus j omega sub s. Suppose that, just to see what happens, maybe somebody says, what if you have a pole halfway between omega sub s over 2 and omega sub s? Or that's 3/4 of the way towards omega sub s. That's now a pole at j, well, let me say s equal j 3/4 omega sub s. Now what we want to do is, suppose we now have this signal that has a pole at 3/4 omega sub s, and we're only sampling at omega sub s. What's that signal going to look like? We now have this pole s is equal to j 3/4 omega sub s. But what do we know about omega sub s? Omega sub s is 2 pi f sub s, or 2 pi over t. So we can write this as j 3/4 2 pi over t. Or this is now j 3 pi over 2t. That's s. Let's see what that does when we map it into the z-plane. That's what it is in the s-plane. Let's map that frequency into the z-plane. And our map is zest, so that's z is equal to e to the st, which is now e to the s. Well, s is j 3 pi over 2t, and there's t. So the t's cancel, and we now have e to the j 3 pi over 2, or that's not e to the j 2 pi, it's not e to the j pi, it's 3 pi over 2. That's now 270 degrees around the unit circle. Or we could say that that's now e to the minus j pi over 2, or a minus 90 degrees. So that z star, its conjugate, is actually maybe in this primary half circle from 0 to 180, or from 0 to pi. What we've seen then is, by sampling at omega sub s and trying to sample a signal that's moving faster than omega sub s over 2, we now have mapped that around to that particular point, or this particular location, depending on how we wanted to write that. Meaning, by mapping or going into the z-plane, omega being 3/4 omega sub s, which is 3 pi over 2t, it now appears not as 3 pi over 2t or 3/4 omega sub s. It's aliased down to a different frequency. It looks like pi over 2t, which is just this conjugate e to the j pi over 2 in terms of its frequency. So instead of looking at something that looks like it's much faster, because we're not sampling fast enough to capture that information, it gets aliased back or reflected back to look like it's at halfway between where we have DC and omega sub s over 2, which is omega sub a of pi over 2t. What happens if somebody said, well, what's the frequency when we're right at the Nyquist? Suppose omega is omega sub n, which is omega sub s over 2. This is now 1/2, and omega sub s is 2 pi over t. This is now pi over t. If we map that through or into the z-plane, that's now e to the j pi, which is really just -1. Or that's 1 at 180 degrees, or one at -180 degrees. And that's where this -1 comes in. That's the highest frequency that we have in our digital system. That's why -1 can look like a very fast frequency in our description, or when we're talking about this point, -1. Or this Nyquist actually provides our primary strip in the S-plane. Meaning if we went back to this particular picture here, you might see textbooks that talk about frequencies in there. That's our primary strip of frequencies that we can identify. If there's a frequency that's outside of that, it actually gets reflected back, and all the frequencies that we see get aliased into that frequency interval from 0 to omega sub s over 2. Which means in a control situation, we probably want to low-pass filter our signals such that frequencies above omega sub s over 2 are attenuated and don't come back and look like something of a lower frequency that might mess us up. So you might hear of anti-aliasing filters. That's the reason those are in place, is so that you don't have, once you've started to sample, you've now basically said, I don't want to know anything about what's happening above the Nyquist. So you would want to have those frequencies attenuated prior to sampling. So now you filter these analog waveforms with this anti-aliasing filter and sample now at omega sub s. Questions on that? So now you maybe know a little bit more about this T. The sampling period gives you the Nyquist frequency. The Nyquist frequency is half your sampling frequency. And you know what omega sub s is. Omega sub s is 2 pi f sub s, or 2 pi over your sampling period. Let's now return, in the time that we have remaining, to this potential situation where we have all three design specs and they may not be consistent, and see if we can figure out what we can do in that particular scenario or in that case. Again, let's just assume for this example that our sampling period is 10 milliseconds, or 0.01 second. And let's say that we have a settling time spec of 500 milliseconds. And let's give us some wiggle room, or say, or less. So now we want to settle in a half of a second. We also want our percent overshoot of 20% or less. And suppose that we want a peak time of 100 milliseconds or less. Now let's see what we can do relative to those three specifications, performance specifications. T, we were told, was 0.1 seconds. The settling time T settle is now N sub ST, which was 0.5 or 500 milliseconds. N sub S then is T settle over T. Or we now have basically half of 100, which is 50. Okay? So the number of samples that we want to experience before we've decayed is 50 samples. And we now can solve for the radius associated with 50 samples in sub S. Or R is now 10 to the minus 2 over 50. And that becomes 0.912. If somebody now gives you a sample or a settling time of 50 samples, you now know you're a little bit beyond 0.9 or 90% of the way towards the unit circle. So that's not that far in, but a lot of stuff happens around 1 and a little bit interior to 1. If we now had dominant poles with a radius of 0.912, that would satisfy our settling time spec of half of a second for this sampling period. Now we also have our percent overshoot spec, and that was given to be 20. We divide 20 by 100, and we take the natural log and square it. We then divide that by pi squared plus the natural log squared of 0.2. We square root all of that, and we end up with 0.456 for our zeta value. And we now need to translate that into an angle. S is minus zeta omega sub n plus j omega sub n square root of 1 minus zeta squared. Z is e to the minus zeta omega sub nt, e to the j omega sub nt square root of 1 minus zeta squared, where we're using e to the st. This piece is our radius. We have omega sub nt, and all of this is our theta sub d. What we don't know is omega sub nt. We don't know omega sub n, but we know that r is e to the minus zeta omega sub nt, which now says that the natural log of r is minus zeta omega sub nt, or solving that for omega sub nt, that's now equal to natural log of r over minus zeta. We can now use this in our theta sub d expression, where now theta sub d is equal to omega sub nt square root of 1 minus zeta squared. But omega sub nt, omega sub nt is ln of r over minus zeta square root of 1 minus zeta squared. And we know r and we know zeta. We can now compute the angle that corresponds to in radians, and that's 0.1798 radians. And that was with r equal to 0.912 from our settling time spec, and our zeta of 0.456 from our percent overshoot spec of 20%. Now, ideally, what we would see is that our peak time spec gives us an angle theta sub d relative to 0.1798. What would we ideally like that peak time spec to be producing? To be consistent with these percent overshoot and settling time specs. Do you have any idea? Pardon? Yeah, it could be the same. Let's say it's on either side. If the peak time spec gives us an angle that's bigger than this angle, are the specs consistent or inconsistent? Let's just figure out the peak time and then we'll figure that out, okay? We'll think it through. Let's see what the peak time tells us and then see if that's compatible or not. Remember, the peak time, if we have an angle, if we want a quicker peak time, which way does that angle need to be? Bigger or smaller if we want to reduce our peak time? Theta sub d is inversely related to the peak time, isn't it? So if we want a smaller peak time, we want our theta sub d to be bigger. Let's see what the peak time specification produces relative to this theta sub d that resulted from a percent overshoot of 20% and a settling time of 1/2 of a second. Our peak time, T sub p, is pi over omega sub d. Omega sub d is pi over time to peak. And we know that the peak time was specified to be 100 milliseconds. So now we know that the omega sub d is 10 pi. How fast were we sampling? I didn't tell you, but I did give you t, didn't I? T I specified Does this seem okay? The peak time spec says we want a damped frequency of 10 pi. We're sampling at 200 pi. Are we okay with our damped frequency relative to the Nyquist frequency? What's the Nyquist frequency in this example? 1/2 of omega sub s, so it's 100 pi. 100 pi is above 10 pi, isn't it? We said we might want, for a rule of thumb, to be sampling 30 times our highest frequency. We're sampling 20 times our highest frequency, so we might have wanted to sample a little bit faster than 0.01 with a sample period. Is that making any sense? This value of sampling frequency, omega sub s, is only 20 times the damped frequency of oscillation, which we are going to just assume is okay for now, for this example. And it's probably fine. You definitely don't want it to be less than or you want to be sampling at least the Nyquist frequency. Now, for that omega sub d, we can generate a theta sub d. Theta sub d is simply omega sub d times t. Omega sub d was 10 pi, t was 0.01. Theta sub d is pi over 10. I can actually sort of remember, since we celebrated Pi Day, pi was March 14th. And we divide that by 10. And now we have, based on our time to peak spec, we have an angle that we want being 0.314. From the first two design specs, we had an angle of 0.1798. Is this angle going to satisfy our peak time specification coming from the first two design specs? Will this be fast enough based on settling time and percent overshoot? We get an angle of 0.1798. Is that fast enough to satisfy our peak time spec, which is demanding an angle of 0.314? How many understand what I'm asking? Is it clear what we're trying? So I would just draw these angles. One is at 0.19, one's at 0.314, or a tenth of the way around to pi. Theta sub d is being spec'd at two different places. We need it to be the fastest in order to satisfy all of these design specs. And which of these are faster? The bigger angle or the smaller angle? If we want this to be bigger, we need to be further in on or around on the unit circle. We need a bigger angle to be faster. T sub p, remember, is related to theta sub d in a reciprocal manner. So the percent overshoot spec does not yield a small enough T sub p. Now remember what pictures we have. If we want less overshoot, which of those lines, maybe I should have drawn them with different colors. Which line has less overshoot, green or blue? Green is thumbs up, blue is thumbs down, and I want you to give me green or blue, which has the least percent overshoot. On the count of 3. Green is up, blue is down, and I want less overshoot. 1, 2, 3. So you need a zeta that's bigger, which is closer to the real line. So that's the blue line. Now, what do we have? We had angles that were maybe here and here, let's just say. We need to satisfy a radial spec, an angle spec, and an overshoot spec, all simultaneously. We learned that the percent overshoot was not enough before. I'm sorry, the percent overshoot spec didn't give us a big enough angle. If we now keep the same radius, but lower the zeta, that's probably not going to help us any, because that's going to actually give us a smaller angle. If you keep the same radial distance and go down on your zeta value, that's probably not the constraint that you want to start contracting. What you'll want to do to meet all three is to actually reduce the radius spec. Now, we're out of time, so I can let you go and I can do this after the fact, or I can just keep going and you can listen, or you can excuse yourself if you want to. I've got about, oh boy, more pages than I thought. So let me just give you the answer, and maybe I'll fill it in with some notes after the fact. What was our R before? The old R was 0.912, something like that. You actually need to pick an R value of, drum roll please, 0.851 to satisfy all three specs. Percent overshoot, zeta, percent overshoot is zeta, settling time is R, and the peak time is the angle theta sub d. I'll try to, after this R, write down where that's coming from, and you can read the notes after the fact.